And then for the next periods, let's do it step by step. So in the first period, we are gonna do the same, and then we need to, since in the first period, right, the t equal 1, we are choosing the same consumption, but I will need to pay the debt that I brought from yesterday. Today, I need to roll over the debt, okay? So that this will be the savings in the first period. And then savings in the second period, I need to pay the first and the second rolling over of the debt, okay? That's it. And then for a generic time period, it is okay. The easiest way to see this was actually in the slides, because we had a table. In the first column, we had the initial choice and the budget constraint for each time period. And then in the right column, we were changing slightly the budget constraints in each period. And that way was clear to see that if the left-hand side is holding, the equality is holding for all the equations, then the right-hand side, the same thing will happen, okay? So this is the, Bernat, that's a good question. And that's what is happening here. R is changing over time. Here we have R1. Here we have, in the second period, R1 and R2. So, and then when we write S in generic form for some T, we are making the product of all the R's, and we are using tau to denote each of the products. And note that R tau, you have R tau, not RT. And that is saying that it changes. Great. Okay. Right. So that was the first question. And then by how much can we increase consumption in the first period and still satisfy the null Ponzi? Right. It's natural to think, okay, since the first initial, the initial choice doesn't satisfy the transversality condition, it has this expression, we are gonna use this in some way, okay? Because note that we have a relationship between S tilde and ST. Also consumption, and we know something about ST, which is here in this expression, okay? But before we do this, let's develop this term. Let's we know that U prime, for example, is 1 over C, right? But we also know how C looks like. Since we know that it satisfies the Euler condition, the Euler equation, initial choices, we know that it satisfies all Euler equation, so we know that it looks like this. We saw this in class. Right? To get this equation, we just take the Euler equation and write for C1, it's a function of C0. C2 is a function of C1, and then we take the C1 that we found before and plug in this new equation. So we do this recursively, and we see that the pattern that emerges looks like this. Okay? We did this in class. It's just using the Euler equation recursively, and then we can write C for any time period as a function of only C0, and then a function of also the variables that the consumer takes as given. Okay, and then we can plug this in the TVC expression, right? It's not, so we can put it here, right? So the limit beta t, and we know that u prime is 1 over c, so it will be 1 over this ct that we found here. That's u prime times st equals phi. So we can cut the beta. We did this in class, right? But there's something different now. In class, this is the limit. Let me write limit t to infinity. In class, this was equal to 0. And then we could multiply both sides by c0. Since in the right-hand side we have 0, we could simply drop this from this equality. But now, actually, if we multiply both sides by c0, we have this. Okay, and then let me just rewrite. Okay, so I took a look at the solution of some students, and there was a C0 missing here because we are used to thinking like that this is the transversality condition, this is equal to 0, and I said that this expression here was equal to phi, and then it's kind of natural for us to think, okay, it means probably that this is going to be equal to phi. But if you do the calculation, you get a C0 here. Okay, that's a very subtle thing. Even when I wrote the problem, I haven't thought about this. And I was talking to a student about this question, and sometimes we know the intuition of the solution, but sometimes the math forces us to consider some things that we haven't considered. Okay, so just to finish, it's necessary to do the math to really know that what you are thinking is right. Okay, so Alejandro, your question is from here to here or before? Okay, so the difference is that I can put the denominator in the numerator, and then I have the -1 here. So yeah, okay, yeah, sometimes we don't see some exponents, right? So I just write it like this because we are used more in the course to write the expression like this. And this is the present value discount factor. So this is saying that the present value of savings in the very distant future is a positive number times the initial consumption. Right. So now this is what we know about ST. And the question asks us by how much we can increase C tilde, right? How great can epsilon be? And we still satisfy the no Ponzi condition, okay? So let's see, how large can epsilon be and still satisfy the null Ponzi condition. The null Ponzi condition for the S tilde is limit is this, right? And we know that S tilde is ST minus epsilon product. It's not one here. It's T. That's S tilde. There's a missing -1 here, right? I forgot to put it. So we write it like this because we know that the null Ponzi condition says that this must be greater or equal to 0, right? So I'm gonna write this expression. I am gonna substitute this S tilde and get this. And we know something about the S, okay? And then this will tell us by how much epsilon can grow. So when we multiply this term by this term, we can cut this product with this product. And then we get this. And then just to be clear, we can kind of make it clear that the epsilon we can put it out of the limit operator. And we know that this is equal to phi C0. Okay, so the null Ponzi condition says that needs to be greater or equal to 0. So we put a greater or equal to 0 here. And then the maximum epsilon we can have is C0 times phi. Okay, so this is the answer to the second part. By how much we can increase epsilon, or how much we can increase consumption in the first period. That's how much we consume in the first period times phi. Okay, so the first time I wrote this problem, I thought the answer was gonna be phi. Okay, but turns out that the math says to us that we need to consider C0, and then I understood it. And the idea is that we are keeping C0 fixed here, right? We have the initial choice, it's C0. And then this is associated to a phi. And the phi tells us how much we are far from the transversality condition, okay? And the idea here is that the phi actually is a function of C0, okay? So why is this the answer? Actually, phi is a function of C0. So we can write phi of C0. Okay. And if you remember the K-Keating problem, this makes total sense. Remember that in the K-Keating problem, if we don't satisfy the transversality condition, we have an infinite number of possible solutions, which are infinite number of possible C0s, okay? And what we learned there is that the higher the C0 is, inside that bound that we can choose, so that all sizes of the cake are positive for all time periods. That's what we did in the second class. The higher is the consumption, the lower is the transversality, the no Ponzi restriction, right? If we make C0 higher, it means that the present value discounted of the size of the cake in the end of the planning horizon is going to 1, is going to 0. And then the higher C0 that we can choose, the highest, is the one that makes exactly the present value of the cake being equal to 0, okay? And since this phi is the transversality, the expression of the transversality condition, that's the present value of savings in the super distant future. If we make C0 higher, we'll have less savings in the super distant future, okay? So and a good case to think here is the following. Here, we don't have any restriction on C0, okay? And if C0 goes to 0, what happens if the Euler equation is holding and we make C0 equal to 0? Remember that the Euler condition says that the consumption in the next period is the time preference times the interest rate, 1 plus R, times the consumption today. So if we make C0 equal to 0, the Euler equation is telling us that we should make consumption equal to 0 in all time periods. And if we do this, it means that we have infinite savings in the future, okay? In the super distant future, because we are using all money just to save. And this would be a case in which phi is going to infinity, right? So we need to consider C0 here in the answer, because phi depends on C0. And one case that we have is that if C0 goes to 0, this phi will go to infinity. And probably, I haven't made the calculations. If you want to make this, may be nice for you to do. This product will go to infinity, okay? I don't know. This is a conjecture. I haven't done this, but it's interesting to think that if you have different C0s, you will have different phis. Yes, Lander, that's a conjecture, okay? I don't know if this is actually true, because maybe the answer, if C0 goes to 0, this phi will tend to go to probably to the total number of wage payments that you have. What I know is the following. So if C0 decreases, phi increases. Because we have more savings in t equal to infinity. Okay, so one nice calculation is to see what happens to this phi if C0 goes to 0. So my intuition was the following. If C0 goes to 0, it means that I'm never going to consume anything. Remember that in each period I get WT, I have the wage, and then I have the earnings of the previous period savings. If I keep compounding, if I make, for example, S1, if I make C0 equal to 0, I will get S1. I will, let me think. Yes, I will get S1 because I will get S0. I'm just thinking the initial condition is S minus 1. I thought it was S minus S0. That's the constraint in the first period. Okay, so if I make C0 equal to 0, I use all the money to save. In the next period, I will have S1 equal to S0 here, but we know that S0 is this. Okay, so I think I already see a pattern. So we have this. Then let me do one more. Okay, I'm just putting CT equal to 0 in all budget constraints. And then I'm gonna try to see how much is ST when t goes to the infinite, to infinite. Infinity. 1 plus R2 S1, and then this is S1. Okay, I'm not gonna do any more, and I will have to think a little more to see how this. So the pattern is like this. So S in T is W in T, and then you go from the end to the beginning in time. So 2, 1, 0, and then the interest rates are compounding in this way. In the first one, we only have R2. In the second one, we have the 2 compounding. And then we always have this here. Okay, Ala. Yes, I'm just kind of. I was thinking, I was doing this kind of just to see where it was gonna be, but this is not part of the question, okay? So what we are trying to do here, I'm gonna write here so you don't get lost. Say you have a choice, you have this choice here, where CT is equal to 0 for all t, and then ST is equal to WT plus 1 plus RT. We are just saving. What happens to, I want to know what happens to the transversality, the expression in the transversality condition. So what happens to okay? I would like to know if this is finite or infinite. Okay, I would like to know if this goes to infinity because this is the phi, right? What happens to this? So first you get an expression for xt, st. We can write xt in general terms here. I will lose some minutes, so I'm not gonna do it. And then we plug here, and this is gonna cut with some terms. For example, this term is gonna cut because this is -1. And here also it's gonna cut with some terms. And then I would like to know if this goes to infinity or to some infinite finite number. Okay. If you want to check this by yourself, you can try to do it. But do you have any questions here? So the original question was asking you how much you can increase epsilon consumption in the first period. Is the answer is that this number is proportional to phi and to C0. Okay. And the idea is also that phi depends on C0. But since we are not thinking about different C0s, you don't need to denote this relationship. Okay, so who thought the answer was phi? Anyone thought the answer was phi? Yeah, I did in the first place also. And the yeah, and the thing is that the transversality condition is this, right? I even wrote in the problem there. So, and then we also showed in class that using the Euler equation, you have this. This is the expression for Ct. It depends on C0. And if this is not equal to 0, you will have a C0 here. That if you want to isolate the limit only depending on things that depend on time, you have C0, you put C0 to the right-hand side, and then you have a C0 there. Okay? That's what we did here. Okay. And then I think the second problem, if you have any questions about this, you answer, you can make them, okay? I think the second one is easier, right? Yeah, okay, so item B, right, of the first question is, why can we increase the consumption in the first period and still satisfy the null Ponzi? Doesn't this contradict the objective of the null Ponzi condition? So the objective of the null Ponzi condition, we motivated like the following. Look, if the consumer can do this kind of Ponzi schemes, then there is no optimal choice, because the consumer can always get more utility just by increasing consumption, right? And then the consumer can increase consumption by an infinite amount, and then you don't have a solution to the problem. But here, the consumer cannot increase consumption by an infinite amount, okay? So this doesn't contradict the objective of the null Ponzi condition, because there's a bound, a limit to the increasing consumption that you can get just by rolling over the debt to the future and never pay it, okay? You cannot increase consumption without limit in this case, okay? So that was the case that initially the consumer was actually losing money, okay? It's kind of the consumer was leaving some positive amount of savings for the super distant future and never consuming it. So the null Ponzi condition doesn't avoid the consumer to not lose money, okay, to not waste resources, okay? What the null Ponzi condition requires is that you cannot consume infinitely without cost, okay? You cannot increase consumption without bounds, okay? So that's why it doesn't contradict the null Ponzi condition. So you just write this and there's no calculations, okay, to be made. So let's go to the second problem here. Now time is discrete. The number of the population size is this. And here we are interpreting the population size as the number of members in the household. Okay, so you have a family, and this family is growing in size. And the idea here is that the household is making choice with the objective to maximize the utility of each member of the household, okay? So this is the number of members in the household. In each time period, the household chooses CIT, that's the choice variable, for each T and each I. Okay, so the household is also choosing how to choose differently for each household member. Initially, the household could theoretically choose a different amount of consumption for each member, okay? And this I here, as it's written here in the problem, ranges from 0 to LT, okay? So the range of I varies over time, okay? You could have more I in more distant futures. And then you have a discount factor, that is rho. And then you have the utility. The utility is increasing in concave. Okay, and then the problem of the household is this. To maximize choosing consumption. So here, this is different from what we saw before because now we have another integral here. Okay, so before we only had u of ct, and now we have this. And the idea is that in each time period, so fix a time period, so fix a term inside this integral, you have the discount factor, and you have, remember that the integral is intuitively the sum. So for a given time period, the household is trying to maximize the sum of the utilities of each household member, okay? All members have the same utility, so that's why you don't have u of ui, you just have u. But then the consumption may depend on each household member, so that's why you have ci. And then we are summing over the household members, that's why we have di here. And then in each time period, you have a different number of household members. That's why the upper limit of the integral is changing. And then that's the aggregate budget constraint of the household. So the aggregate budget constraint of the household only depends on total consumption. Okay, so that's why you don't have CI here. And then the total consumption is defined as the sum of the consumption of each household member. The total consumption in T is just the sum over CIT over I. Okay. Right. So for a given T and choice of total consumption, big CT, argue that the household optimally chooses to split consumption equally between each household member. What property of the instantaneous utility is important for this result? Okay, last class we already talked about this. So the important property is concavity. Is this? Oh wait, I cannot see what I wrote. Can you hear me, guys? Can you see what I wrote in black? Okay, I cannot. So I'm gonna stop sharing and start sharing again. Okay. I'm gonna stop sharing and start sharing. Okay. So the important property is this, and what I want you to talk about this here is, as I mentioned, what I want you to talk about is the marginal utility idea, right? Because the concavity says that the marginal utility is decreasing. So for example, oops. Say you have household member 1 and member 2, and then say that you have the consumption of the first household member for some time period greater than the consumption for the second household member, and then you have that the marginal utility of the first household member is lower than for the second household member, right? And that's concavity. That's concavity makes the marginal utility decreasing with respect to C. So if we have a higher C, we have a lower marginal utility, okay? And then if you take, Alejandro, that's a good question. So we are choosing different, so Alejandro is asking, how can this happen if all members have the same utility function? They have the same utility function, but they don't necessarily have the same consumption. So in this example, we are giving consumption for the first member higher than for the second member. And then the utility of the first household depends on the consumption of the first household, and the utility of the second household depends on the consumption of the second household. Okay, so the utility function is the same. It doesn't mean that the utility of the households for all choices are the same. Okay, the utility is a function. It depends on the choice. Okay, so what we are saying is the same for households are the utility functions. So if you take some amount from 1 and give it to 2, the loss in utility for household member 1 is the marginal utility, right? Remember, the marginal utility is how utility changes if you increase consumption by a very small amount or decrease by a very small amount, okay? So the loss of 1 is his marginal utility, and gain of 2 is the marginal utility. So this means that the total utility increases if we make this reallocation. Okay, so you don't need to make calculations. You just need to say this. Okay, if the guy who has more consumption has a lower marginal utility, so if you take some consumption from this guy and give to the other guy who has less, the loss of the guy who loses is lower than the gain of the guy who wins, who gets more consumption. Okay, and that's only because of concavity. Okay, so okay, now let's go to B. Remember that at any time you can ask me a question if you want. So let's go to B. Rewrite the problem using the variable big CT. No, without using big CT, right? Use the previous result and write the problem without using the variable big CT. Use only per capita consumption instead. So since consumption is the same for all members, we can write, now we can take the I out of the variable because they are all the same. And then, okay, the problem is asking us to rewrite all the problems. So the problem has kind of three components, right? The objective function, the budget constraint, and the definition of total consumption. So let's rewrite the objective function. And we had CI here. That's going to be just C instead of CI. So the sum of the utilities of households will not depend on I here anymore. The consumption doesn't depend on I. So we can take this out of the integral. It's not T here, that's LT. We can write it like this, or I can put a 1 here. Okay, doesn't matter. And this integral is just going to be LT, right? It's the if you take the derivative of a variable that doesn't depend, let me think. Yeah, so I like to interpret this. Just a second. Yeah, the integrand is 1, right? So we are taking the integral from 0 to this. The integral is the area. So the area is LT times 1, which is LT. So this is UCT LT. Okay. And so we can rewrite the objective function as the maximum of E rho T LT CT dt. And we know that LT grows by a fixed proportion. So it looks like this. Yeah, it's not CT, it's U of CT as it's written here. I wrote CT here, but actually it's U of CT, right? It was a mistake. U of CT dt. So that's the same objective function that we had in the model that we saw in class. Okay, and we have 3 objects. We already have solved this one, and then this one, CI only depends now, doesn't depend on I. So we can do the same here. CT is the integral, the sum of all the consumption of individuals, but this only depends on T, doesn't depend on I, so I can do this. Which is LT of C, big LT times small c, and then the budget constraint. This item only asks us to get rid of the big C, so we can just write the aggregate budget constraint in terms of aggregate, not in terms of per capita. And that's the answer, okay? So the problem is to maximize this subject to this, okay? Choosing small c. And then subject. And then just to make clear what is the choice variable, we can do it, write it here. Okay, that's how Acemoglu denotes. It uses this. In all the problem of the books, they write it like this. They use these brackets here. And Barrow doesn't write anything here. So I like to write because it makes clear what the choice variable is. And finally, derive the per capita budget constraint. I already did this in class, okay? So all we want to do is to, instead of writing big A, just write small a. And what is the relationship between small a and big A? Is that big A, small a is big A times divided by L, population size. So if you take the derivative with respect to time in both sides, we have this. And then we need to use the quotient rule. It will be A dot LT minus ATL dot divided by L squared. I can cut the L in the first term, and AT, L dot T over L. We know that this is equal to N. And then A dot divided by L. We have A dot here. So if we divide this by L, we have this over L, this over L, and this over L. So it will be RT plus small wt. Sometimes it's hard to distinguish my big letters and my small letters, but this is the big W here, up. And this is the small w down here, minus C minus ATN, which is the part that is left here. And then, oops, there's a missing A here, right? Because it's big A divided by L, that's small a. Okay, so we already did this in class. I'm just doing it again for you to have the answer. I'm gonna send you these answers, okay? Do you have any questions about this? So if you don't have any questions, let's take a 10-minute break. And I need to drink some water. And then we can go back and we are gonna continue with the neoclassical growth model in continuous time. Okay, guys, so see you in 10 minutes. Sorry?
Hello, Professor.
Hi.
For the sub question B, it says use the aggregate term to express the maximum problem. But I noticed that in your final answer, there is a small per capita term. That is the consumption. Can you also replace the per capita consumption into aggregate term?
Yes, you can. That's what we do in the class. When we write the problem, we write with all the variables in per capita terms. So here I'm not asking you to do it, but you can do it, and these two ways of writing are equivalent. So
okay,
you can do it.
Thank you, because I replace all the aggregate, all the per capita term with the aggregate term. So
okay, but did you include the n?
Yes, I include
so that's
that
right.
in my.
Okay.
Thank you.
Thank you. Hi guys, sorry for being late 2 minutes, but now I'm back. Let's jump through the slides. Right, so last class we started talking about the general equilibrium, right? We spent a lot of classes talking about the consumer, and then we talked about last class we talked about the firm. The firm is relatively simple. The problem of the firm is just a static problem, so it's simple to solve the problem. And then we have the optimality conditions, and after we have the optimality conditions, we start using the general equilibrium idea. And the general equilibrium has to do with the fact that you have a labor market and you have an asset market, and then the supply and demand for labor must be equal, and the supply and demand of assets must be equal, and assets can become capital in a one-to-one relationship. So 1 unit of asset becomes 1 unit of capital, and then you have these general equilibrium conditions for the asset market. And then now we are gonna transform this system of differential equations that describe the optimality conditions for the consumer. We're gonna include the general equilibrium idea, and we also need to include the optimality conditions of the firm, because the firm makes optimal choices depending on the variables that make the general equilibrium hold, right? So the interest rates is the variable that adjusts so that you can have supply and demand of assets or capital equal to each other. And in this model, this is the simplest model. We don't have supply of labor from the consumer, but we have demand of labor from the firm. And the consumers are all supplying labor inelastically. But remember that the population grows over time, so that the wage rate adjusts itself. So you have demand equals supply of labor, okay? And then we need to write this, and then we did all of these calculations that you are seeing now. We did this in the previous class, and we did this to get to this last relationship. It's the law of motion of capital in per capita effective terms, right? Remember that K hat is equal to big K over LT, right? And T is the labor augmenting productivity that grows by the strict proportion X that is here. So we are gonna see that in steady state, these variables in steady state are fixed. So that's why we want to write them. We want to write all the equations, the law of motion of capital and the optimality conditions for the two types of agents in terms of these hat variables, because this is the variable that is going to be constant in steady state, okay? And this is the law of motion of capital, and it takes into account X, N, and delta, okay? Okay, so we had the Euler equation, and we saw that it depends on R and rho. We already have an optimality condition regarding R, that if I come back here, the firm's optimal choices is such that the marginal product of capital equals small r plus delta. So we can isolate this R. So small r is the marginal product of capital minus delta. So we have marginal product of capital minus delta. Let me go one step here. So 1 over remember it is RT minus rho, right? And here I am writing, we want to know the behavior of per capita effective consumption. Okay, so it's the C hat. So it's C hat dot. Okay, the order of the operations kind of matter. Okay, so C hat dot is different from C dot hat. Okay, we want to know how C hat changes over time. So it's the derivative of C hat with respect to time divided by C hat. Let me add a page here. So you have this relationship. I'm going to show you this to you now, that C hat dot over C hat is C dot over C, small c dot over small c, minus x, okay? And the interpretation for this, that C hat is C divided by something that is growing over time, right? Remember that C hat is small c over t, and t grows over time at this rate x, so the growth of C hat is lower, okay? And let's see. C hat t is Ct over big T. We want to show C minus x. So the relative change of the hat variable, oops, there's a hat here. So the relative change of the hat variable is the relative change of the not hat variable minus the variable that we are dividing. So we just need to take the derivative of the two sides here with respect to time. Let's use the quotient rule, C dot T, TT, CT, T dot T over T squared. So this is C dot T over T minus C hat T over T dot T over T, T. That's very similar to what we did before, right? So actually it's just the same. If you change the symbols, you get the same result because we are doing the same calculation. We know that this is x. T dot over T is x. That's the growth rate of T. And what actually we want to know is C hat dot over C hat. Okay, so I'm gonna divide this right hand side by C hat too. Minus, I just have x here. And wait, I have something open here. Let me close. That is making a noise in my ear. Okay, so, and then C hat is small c over big T. We're gonna use this here. Small c over big T So you can cut big T. And then we have what we want. Okay. So we know, we just showed this first equality, and we have this, which is this here, minus x. I can multiply theta and divide by theta here. So I can put theta 1 over theta in evidence, and we have this relationship. So this is the Euler equation, already including the general equilibrium idea and the optimality choice, the optimal choices of the firm, okay? Because we have the fact that I will under. We have the fact that f prime k minus delta is r, okay, is the interest rate from the optimality conditions of the firm. And we add this theta x here because we are now having the relative change of c hat, okay? Notation. Lander is asking about notation. Okay, so no problem, Lander. That's a crazy notation because we have c hat dot, okay? So c hat of t is c over big T, okay? Yeah. And so the derivative of c hat dot, the derivative of c hat with respect to time, remember that we are using the notation that the derivative of any variable with respect to time, you write a dot above the variable. Since the variable is c hat, we have c hat dot, okay? So that's the notation here. Remember that the relative change of a variable in time is let's say the variable is x, it is x dot over x, because that's like final x minus initial x divided by initial x, right? The percentage change in continuous time, it's x dot over x. So the relative change of x hat is this, is c hat dot over c hat, okay? You just make x equal to c hat here, okay? Is this your question, Lander? So c hat dot, right? That's your question? You wanted to see what I just said? Okay. Remember that this T is the labor productivity. The production function is f of k L, and then this L is multiplied by T. Okay, so that's the T. Yes. Yes, Alejandro. So okay, that's a labor augmenting productivity. And it grows by this fixed proportion that is, we call x, that this may be greater or equal to 0. Okay, if you make it equal to 0, you have the model without technological change. Okay, this is labor productivity, but we call it technological growth or something like this. Okay, technological. So okay, so we are trying to transform these three equations in general equilibrium, and in terms of the aggregate economy in general equilibrium and with the optimality choices of the firm. So we also have the TVC. So the TVC is this here. And okay, we want to write it in terms of hat variables. Okay, everywhere in which where you find A, we're gonna write K. So this is, let's do just one step before. This is, let's just switch A for K, KT, exponential, integral. Remember that small r is marginal productivity minus delta in hat, in k hat. Okay, so small r is f prime k hat minus delta. We can put it here. And then we have also minus n, that is here. But it's not t, is v. So I'm gonna write, it's not, that's the, it's a v, dv. So now we switched a for k, and we also plugged the condition for r. Okay, and now we just want to have a k hat here, because we have k without hat here, we have k with hat here. So we have this relationship, right? K hat is equal to small k over big T. Big T is e to the power of xt. So I can put big T in the numerator and switch the power of the exponential. And we have this relationship. Okay. Big T is ext. And okay, so this k here, we can write k. Yes, let me do it step by step. So kt is k hat t ext. Okay, so we can plug k hat e to the power of xt, and then we would have exponential of something times the exponential of the integral. We can, the sum of the exponentials is the multiplication of the exponentials is the exponential of the sum. So this here, let me do it step by step. I'm gonna substitute this k here, here. Then we have k hat. So it will be k hat t exponential of xt times exponential of minus something here. Okay, just gonna write a dot because I don't want to repeat everything. So this is the limit exponential of xt minus the integral. Okay, and look here, that's the answer. I can put these x, it shows up here. Okay, is this step clear for you?
What? Yeah, these x inside the integral, because use a mathematical rule, or I don't know why.
So we have time k hat e xt minus it's better to do it slowly, and minus n dv. Okay, that's what's inside the exponential. Let me just check. Yes, f prime k hat minus delta minus n, f k hat minus delta minus n, and then xt. And the thing is the following, right? That's not so straightforward. Note that the integral from 0 to t of x dv, what is the function that if you take the derivative with respect to v, you get x? That's x times v, right? Plus a constant, it can be, okay? But since we are doing a definite integral, we don't need to plug the constants, okay? So that's, we can write it like this, xv, that's the antiderivative. And then we evaluate in the upper limit minus it in the lower limit. So it is xt minus x times 0, which is xt. Okay? So just one thing. Do you know why if you have a definite integral, which means an integral that goes from a lower bound up until a upper bound in which both are finite, okay? Do you know why when you use this, you don't need to think about the constant? Okay? Okay, team. So let me be one step clear here. The antiderivative of x is xv plus a constant because the derivative of xv plus a constant with respect to v is x. Okay, so Lander, that may be the graphical interpretation. I need to think about the graphical, but look at the algebraic interpretation is very simple. So the minus it in lower constant. Value of evaluate e minus constant, and then minus this function evaluated lower bound. That's x0 minus constant. I can cut constant and constant. Okay, so the answer is just xt. Okay, so every time you are solving an integral and you have a definite integration limit, so from a finite lower bound to a finite upper bound, you don't need to think constant. Right. So let's is equal to this. minus the same, let me copy. That's small. Yeah, we don't have this minus here. Let me try to put a bigger letter. Okay. And then I can put the two integrals together, right? So minus d minus n minus x dv. And notice that we have minus x here, but we have a minus here. So it's a plus x if you split the integral. Okay, so that's why I can go from here to here. Okay, so first we started with k without hat, and if I put k with hat, I need to include also the exponential of xt, and then I can put this x inside the integral, because I can do the opposite operation and transform this xt in an integral. Okay, and the intuition is that if you have a constant x times time, that's a constant times time, that's the integral of the constant without the time in the expression. Okay, so this now is the transversality condition in terms of capital hat. Alejandro, we want to write all the equations in terms of k hat. So we want to describe the economic system in terms of per capita variables in effective terms. So these are just a bunch of algebra to get to this. And that's done. Okay, so finally we are done. So we have the Euler equation, including the firm's optimality condition and the general equilibrium. We have the law of motion of capital, per capita capital in effective terms. Okay, effective means per units of productivity of labor. Okay, that's k hat. And the transversality condition. And these two equations describe the joint behavior of consumption and capital. Okay, so take a look at this system of equations. Those are differential equations. Okay. For example, this is a differential equation in terms of c hat. Okay, because we have c hat dot in terms of actually it depends on capital. Okay, and capital itself is a differential equation. Okay, because we have k dot here, k hat dot, and we have k hat, and we have k hat here. Okay, so this is clearly a differential equation. And we also have consumption here that depends on capital. So this is a system of differential equations because the derivative of a variable depends on the variable itself. Okay, the derivative of a variable with respect to time depends on the variable itself. And it also depends on consumption that depends on the variable that is capital. Okay, so these two here is a system of differential equations. And this is not a differential equation because we don't have the derivative of some variable with respect to time here. Okay, so this is just a condition. This is the transversality condition. But the important thing is that this is a condition associated to the variable that is in the system of differential equations. Okay, we would like to solve this system for k hat and for c hat. Okay, we already know how to solve the system for c hat. Okay, because this is c hat dot over c hat as a function of time. And here in the right hand side, we have nothing associated with consumption here. We only have something associated with capital. So we can solve for consumption as a function of capital. Okay, but we're not going to do this because we're going to have a nice, interesting graphical interpretation for the system of differential equations. Okay, but if you wanted, you could solve for c hat, and you would have something. The solution will be a function of c hat 0 and these variables that are here. Okay, so just to be clear, remember that the problem set that you have now, you saw that c dot over c equal to 1 over theta minus rho. You can solve this, and the solution is c0 exponential of rv minus rho dv from 0 to t. Okay, so if you wanted, you could do the same here, because now instead of just c dot, you have c hat dot as a function of something that depends on time. Here it is capital. Okay, but we're not going to solve this differential equation for c because we want to have this system of equations that depend on consumption and capital. Yes, Pablo.
And then we should plug that result on the second equation and do it again, the same process to find k hat dot.
Yeah.
Okay.
That's a great question, Pablo. You could solve this, plug it here, and you would have here, you would have c hat of 0, and you also would have f prime of k hat here. But the thing is that we don't know how to solve this. This is not a linear differential equation with coefficient variables, for example, which is the type of equation that we know how to solve. Because we have k hat dot here, and we have a function of k hat. Remember that if the production function is the Cobb-Douglas production function, so if f of ktl is some parameter times alpha tl1 minus this, we know that f of k, if I'm not wrong, that's, I may make some mistake here, but I think that's a k of alpha, right? So this will be k hat dot, and this will be a function of k hat to the power of alpha. Yes, Pablo, thanks. So my question is if this big A is still here. I think it is. Yes, it is, because we don't divide by the production function itself, I think. Okay, so if we use the Cobb-Douglas here, we would have k hat dot as a function of k hat to the power of alpha. And this is a nonlinear equation. So we don't have an analytical solution for this. Okay, but we will be able to understand a lot about this system of equations using graphical analysis. Okay, and okay, so just one more thing. This is a system of differential equations. We have the initial condition for K. That's given, that's a parameter, remember? K0 is a parameter, so K hat 0 is a parameter because we just need to divide it by T, okay? And we have an initial condition for this system, and we have a terminal condition, okay? And that's what this economic system will look like. This is a dynamic economic system, okay? So we did all these calculations to get to this here, and this will describe the economy. And this will describe how the economy will converge towards the steady state, just like as we saw in the Solow model. Okay? So here is just a proof that the steady state is a situation in which the variables are constant. Okay? So if let's define the steady state as a situation in which the rate of changes of hat variables are constant over time. Okay, it doesn't change over time. So we denote it by the rate of change of K hat is gamma K hat star, and for C we have gamma C hat star. And then we are going to show that if we have a situation in which variables grow by a fixed proportion in this economic system, then they must be constant. Okay, growing by a zero rate is a constant growth. Okay, so in the steady state of this economic system, the variables in hat are fixed. Okay, so this is a proof by contradiction. We will first assume that the growth rate is positive, and then we see that this doesn't satisfy some of the conditions that we have in the dynamic system. And then we're gonna do the opposite. We're gonna assume that it's negative, and we are gonna get to a contradiction also. And then in the end, we're gonna conclude that it must be the case that the variables are fixed in the steady state. Okay? So assume that capital grows by a positive rate in steady state. Okay? And this must mean necessarily that K hat goes to infinity. Okay? Because look, K hat dot over K is positive. Remember that K hat dot over K hat is a number, for example, 1%. Okay? And it means that capital grows by 1%, and then in the next period, capital is going to grow by 1%, but now we are increasing a variable by 1% that is higher than before. Okay, so remember that this generates an exponential growth. So if you have a variable that grows by a fixed proportion in all time periods, and this is positive, this variable goes to infinite. Okay, so we saw some variables that have this property here in this model. For example, population. So in this model, population grows by a fixed proportion, and it goes to infinity when time goes to infinity. Okay, this variable tends to infinity. So if this happens, we're gonna have K hat going to infinity. Remember that by INADA, this means that the marginal productivity of capital is going to 0. And we're gonna find that this is a contradiction in the transversality condition. Okay, so let's just try to see the transversality condition here. This variable is going to infinity. What is the other variable in this expression that depends on capital that is going to infinity? Is the marginal productivity, and we are seeing that this is going to 0, right? Because of INADA. The marginal productivity of capital goes to 0 when capital goes to infinity. So this goes to 0. Let me think here just one thing. So if this goes to 0, this will be higher. I mean, this is going to become negative. Yes, because we have 0 minus something positive. Okay, and this is negative. So you have a negative number here, and then you have a negative number here. This is positive. So this is going to infinity, and this is going to a positive number. That may be even infinity. So it's infinity times infinity, or infinity times a positive number. That cannot be equal to 0. Okay? That's the hand-waving proof of this. I'm just
Sorry,
pointing.
can you say again why the exponent is positive?
Shame. Because this is going to 0. This is a negative number. So there will be a time period that for all time periods later than this term is negative. So what's inside the integral is negative. But this is multiplying by a negative number, so it is positive. Okay? This is a hand-waving proof. Let me prove it to you mathematically. Okay? We have 2 minutes. So that's the proof here. So if f prime of k hat goes to 0, there must be some time period, t star, such that delta plus x plus n becomes greater than the marginal productivity of capital for all time periods after this threshold time period. Okay? And then we can rewrite the transversality condition, and we can split the integral from 0 to t star and from t star to infinity. Okay, I'm just splitting the integral because the integral goes from 0 to infinity. I can say that this is the same as the sum of the integral that goes to 0 to t star plus the integral from t star to infinity. Okay, it's not infinity, it is t. So, but this holds for any t greater than t star that I'm taking. Okay, and then the exponential of this integral is the exponential of the sum of the integrals. I can also split the exponential. So I have the exponential of the integral that goes from 0 to t star and the other one. Okay. Now, as t goes to infinity, this is not going to change because it doesn't depend on t. Okay. And we know that all of these terms here are negative inside the integral. And then we have the minus here. So this must be going to infinity because we are integrating an infinite number of positive numbers. Yes, if I put the minus inside here, it's as if we are integrating from t star up until infinity, always positive numbers. So this goes to infinity, okay? And so that's the formal proof, okay? You just need to split the integral here, okay? That's a formal proof. You don't need to care about this a lot. It will not be in the exam. That's just a formal proof, okay? Because if you want to work with a model, if you we already learned this right from the problem set. If you just think about the intuition, you may get some things wrong, okay? So you need to formally prove something sometimes. Okay, so I'm just gonna, it's 2 p.m., but let's just finish this proof, okay? Because it's always bad to stop something in the middle of it, okay? So now we already saw that the growth cannot be positive. Let's assume that it's negative. So it must mean that capital is going to 0. So it is always decreasing by 90%, by 10%, 10%, 10%. It's going to go to 0 sometime. That's a point, okay, in the time infinity. So it means that the marginal productivity is going to infinity. And then this is going to be a contradiction using the Euler equation, okay? And the Euler equation is this one. And if this is going to infinity, all the other terms that depend, I mean, they don't depend on time, okay? So it means that the growth rate of consumption is going to infinity, okay? That's a contradiction because we have assumed that the growth rate of consumption is fixed. It doesn't depend on time, okay? So this means the following. If you have a situation in which the growth rate of consumption is fixed, you can now not have the growth rate of capital being negative, okay? So that's a proof that it cannot be neither positive nor negative. So the growth rate of capital is 0, okay? So since we are done with the time, that's it. So in the next class, what we're going to start proving? We proved that the rate of growth of capital is 0. We are going to prove that the growth rate of consumption is 0, okay? So this is a formal proof that in the steady state, the variables hat, so per capita variables in terms of labor productivity, they are constant, okay? So thank you guys, see you on Wednesday. If you have any questions, I can be here for 2 minutes and wait for you. And if you don't have questions, see you in 2 days. Bye team, bye Joan, Bernat. Bye guys. Bye Lander. Bye Liv.